Revolutionizing communication, Meta's two new studies demonstrate 80% accuracy in real-time thought-to-text decoding. Date, February 14, 2025. Location, Paris, France, San Sebastian, Spain. Introduction. Meta, the parent company of Facebook, has made a significant leap in the realm of neurotechnology, unveiling two pioneering studies from its fundamental artificial intelligence research FAIR lab. These studies demonstrate an impressive 80% accuracy in decoding thoughts into text using non-invasive brain recordings. This breakthrough holds promise for individuals who have lost their ability to communicate due to neurological injuries. Overview of the research. In collaboration with the Basque Center on Cognition, Brain and Language in Spain, the studies involved 35 healthy volunteers. Researchers recorded brain activity while these participants typed sentences utilizing advanced techniques like magnetoencephalography (MEG) and electroencephalography (EEG). The newly developed AI model termed Brain 2 QWERTY outperformed traditional EEG methods by at least 200%. Decoding up to 80% of the characters typed. Key findings. 1. Decoding mechanism. The first study focused on translating brain signals into text. Researchers successfully reconstructed full sentences based on neuronal activity, leveraging deep learning techniques to interpret the magnetic fields produced during typing. 2. Understanding language production. The second study explored the cognitive processes involved in language formation. It revealed that the brain organizes language hierarchically, starting with abstract concepts and progressively translating them into specific words, syllables, and letters, all through a dynamic neural code. Implications for communication. These findings have profound implications for individuals with communication impairments, such as those suffering from brain lesions or traumatic injuries. Non-invasive brain-computer interfaces could potentially restore communication abilities. However, practical challenges remain, particularly concerning the cumbersome nature of MEG equipment, which requires users to remain still in magnetically shielded environments, limiting its clinical applicability. Timeline of events. 2017, Meta, then Facebook, announced ambitions for a brain-reading device capable of converting thoughts to text. February 2025, the groundbreaking studies were published showcasing substantial progress towards this ambitious goal. Differences between sources. While all sources acknowledge the significance of these findings, they diverge in their focus on practicality. Source 1 emphasizes the collaborative nature of the research and ongoing partnerships in neuroscience. Source 2 highlights the life-changing potential of the technology but notes the impracticalities of current equipment. Source 3 provides a technical overview discussing the limitations of non-invasive technology compared to invasive brain-computer interfaces and emphasizing the research's ongoing nature rather than immediate commercial applications. Detailed observations from sources. Source 1, Meta's official blog. Meta's blog post summarizes their approach to decoding language from brain activity, emphasizing their commitment to open and reproducible science. The collaboration with the Basque Center on Cognition, Brain and Language has led to significant breakthroughs in understanding how AI can advance human communication. Meta announced a $2.2 million donation to the Rothschild Foundation Hospital to support ongoing research in this area. Source 2, PC Gamer. This article provides a more casual overview of the studies, referencing the initial enthusiasm that Meta had shared back in 2017 regarding brain typing technology. It discusses the practical challenges of using MEG scanners, which are large and expensive, and the limited sample size of participants. The piece also underscores the potential life-changing applications of this research for individuals with communication difficulties. Source 3, MIT Technology Review. In a more technical analysis. This source highlights the initial ambitions of Facebook to create a consumer brain reading device and contrasts them with the current state of research. It notes the limitations of the non-invasive techniques used, which do not yet translate into practical applications for patients. The study's insights into hierarchical language processing in the brain could inform future AI developments, ultimately advancing the field. Conclusion: Meta's recent studies represent a groundbreaking advancement in the intersection of AI and neuroscience, potentially transforming communication for individuals facing significant challenges. As researchers navigate the technical and practical hurdles, the ultimate goal remains clear: to enhance human interaction through innovative technology. The commitment to open-source AI further suggests that the broader AI community may contribute to the real-world applications of these technologies, paving the way for future breakthroughs in communication and cognitive understanding. The content presents a fascinating development in the realm of neurotechnology and artificial intelligence, specifically regarding Meta's studies on thought-to-text decoding with an accuracy of 80%. Here are some counterintuitive insights derived from the content. 1. Impressive accuracy at limited practicality. While achieving 80% accuracy in decoding thoughts into text seems groundbreaking, the practical implications of this technology are significantly hampered by the cumbersome nature of the equipment used. The magnetoencephalography (MEG) scanner required for this research is expensive, heavy, and necessitates users to remain completely still in a shielded environment. This contradicts the often held assumption that technological advancements lead to immediate and practical applications in real-world scenarios. 2. The use of healthy volunteers. The studies were conducted with 35 healthy volunteers typing sentences without any known speech impairments or neurological injuries. This raises questions about the applicability of the findings to individuals with actual communication difficulties. It is counterintuitive to think that research aimed at developing technology for those with communication impairments would not directly involve the target population from the outset, thus creating a gap between research intentions and real-world applications. 3. Dynamic neural code versus traditional understanding of language processing. The research revealed that the brain organizes language production hierarchically, moving from abstract concepts to concrete words and letters. This challenges traditional views of language processing, which may not fully account for the dynamic and layered nature of thought transformation into language. It suggests a more complex interaction within the brain than previously understood, indicating that our comprehension of cognitive processes might need to adapt significantly in light of new findings. 4. The path to commercialization is distant. Despite the excitement surrounding these breakthroughs, the researchers themselves express skepticism about the technology's path toward commercialization. The leader of Meta's brain and AI research team explicitly states that the current system is not oriented toward products due to the technical difficulties involved. This contradicts the common assumption that successful research automatically translates into consumer-ready products. 5. AI requires robust data but still faces limitations. The studies emphasize that deep neural networks can uncover remarkable insights given high-quality data. However, they also highlight that the current model only achieves a 32% error rate, suggesting that even with advanced AI, the technology is still far from perfect. This underscores the counterintuitive notion that more data does not always equate to flawless outcomes, particularly in complex fields like neuroscience, where human cognition operates in nuanced ways. 6. Long-term collaborative efforts over quick fixes. Meta's commitment to open-source AI and collaboration with various research institutions reflects a shift from a quick-fix mentality to one that values long-term partnerships in scientific advancement. This contrasts with the often expected rapid commercialization of technological innovations and instead suggests that real progress in neurotechnology will require sustained collaborative efforts across disciplines. 7. The challenge of non-invasiveness. Non-invasive techniques are generally perceived as safer and more user-friendly compared to invasive methods. However, the studies reveal that non-invasive approaches like MEG can still be impractical due to their operational constraints and the requirement for specialized environments. This brings into question the assumption that non-invasive technologies are always the preferred solution in medical technology. 8. Potential for AI to inform human intelligence understanding. The research aims not only to develop technology for communication but also to deepen the understanding of human intelligence itself. This dual focus is counterintuitive as it suggests that advancements in AI may not solely serve practical applications but also contribute to fundamental scientific knowledge about human cognition which may not yield immediate benefits for users. These counterintuitive insights highlight the complexities and challenges faced in translating groundbreaking research into practical applications, emphasizing the need for a nuanced understanding of the interplay between technology, neuroscience, and human cognition. Important content overlooked in Meta's thought-to-text decoding studies. Meta's recent studies on brain-to-text decoding using AI have generated significant excitement, but certain key aspects are often overlooked in discussions about their implications and limitations. Understanding these nuances is crucial for grasping the full impact of this research on future applications, particularly in neurotechnology and communication restoration. 1. Scope and limitations of current research. One notable aspect that tends to be underemphasized is the scope of the study participants. The research was conducted with 35 healthy volunteers who typed sentences, which raises questions about the generalizability of the findings to individuals with actual communication impairments such as those suffering from traumatic brain injuries or neurological conditions. While the accuracy of 80% in decoding thoughts into text is impressive, the real-world application requires testing on a population whose brain activity might differ significantly from that of healthy individuals. This limitation is significant because it leaves open the question of how effective the system will be for its intended users, those who truly need it. 2. Technical practicality and accessibility of equipment. Most discussions highlight the innovative nature of the brain 2-QWERTY model but often overlook the practical challenges related to the equipment used. The magnetoencephalography (MEG) system necessary for this research is expensive, approximately $2 million, and requires a magnetically shielded room along with the subject remaining still during the scans. This presents a stark contrast to the notion of a portable or user-friendly device which many might envision when considering thought-to-text technology. The impracticality of current systems poses a significant barrier to clinical application, meaning that while the research is groundbreaking, translating it into a usable product for those in need is far from straightforward. 3. Neural code insights and hierarchical language processing. The studies reveal insights into how the brain organizes language production hierarchically, starting from abstract concepts down to specific letters. This dynamic neural code is an important finding as it suggests that our understanding of language processing is evolving. However, the significance of this hierarchical processing is often glossed over. By understanding how the brain sequences thoughts into language, researchers can enhance not only neurotechnology but also AI models that mimic human cognitive processes. The implications for enhancing AI's natural language processing capabilities could be vast, yet this aspect is not always highlighted in popular discussions of the findings. 4. Collaborative nature of research. The collaboration with the Basque Center on Cognition, Brain, and Language (BCBL) is another critical element often overlooked. The interdisciplinary nature of this research underscores the importance of partnerships in advancing scientific knowledge. Meta's commitment to collaboration and $2.2 million funding to support ongoing research efforts demonstrate a long-term vision for integrating neuroscience and AI. This collaborative approach could foster more robust advancements in understanding brain function and developing practical applications, yet its importance is frequently overshadowed by the focus on technological achievements. 5. Ethical considerations and future directions. While the potential applications of thought-to-text technology are exciting, the ethical implications surrounding its use are rarely addressed. Questions regarding privacy, consent, and the potential for misuse of such technology in manipulating thoughts or unauthorized mind reading are critical to consider. As technology progresses, these ethical concerns must be part of the conversation. ensuring that advancements do not outpace the development of appropriate regulatory frameworks. Future research must prioritize these discussions alongside technical advancements to ensure responsible deployment of such powerful tools. Conclusion: Meta's studies on thought-to-text decoding signify a promising leap in neurotechnology and AI. However, crucial elements such as the limitations of participant demographics, practical challenges of technology deployment, insights into hierarchical language processing, the collaborative nature of research, and ethical considerations are frequently overlooked. Addressing these aspects is imperative for a comprehensive understanding of the implications of this research, guiding it toward responsible and effective application and enhancing communication for those in need. 1. Decoding mechanism. The first key finding of Meta's studies is the development of the AI model called Brain 2 QWERTY, which successfully decodes thoughts into text with an impressive accuracy of 80%. This breakthrough was achieved through non-invasive brain recordings using magnetoencephalography (MEG) and electroencephalography (EEG). The studies demonstrated that the model could reconstruct full sentences based solely on brain signals, a significant improvement over traditional EEG methods, which were at least 200% less effective. This advancement opens up new possibilities for brain-computer interfaces aimed at helping individuals who have lost communication abilities due to neurological injuries. 2. Understanding language production. The second study provided insights into the cognitive processes involved in language formation. It revealed a hierarchical organization of language production in the brain, starting from abstract concepts and progressively translating them into words, syllables, and letters. This understanding of how the brain organizes and processes language has implications for both neuroscience and artificial intelligence. By decoding the brain's dynamic neural code, researchers can better understand how thoughts are transformed into language, potentially informing the design of more sophisticated AI systems that mimic human-like reasoning in communication. 3. Implications for communication. The research has profound implications for individuals with communication impairments, particularly those with conditions such as ALS or traumatic brain injuries. The development of non-invasive brain-computer interfaces could restore communication abilities, enhancing the quality of life for affected individuals. However, practical challenges remain, including the cumbersome nature of the required equipment and its current limitations in clinical environments. The studies highlight the need for continued research and collaboration within the neuroscience community to overcome these barriers and translate laboratory successes into real-world applications. 4. Challenges and future directions. While the studies present promising advancements, they also underscore the challenges that lie ahead for practical implementation. The MEG equipment used is expensive, requires users to remain still in shielded environments. And the research participants were all healthy volunteers without communication impairments. Future research must focus on testing the AI model in more varied and clinically relevant populations to determine its efficacy in real-world settings. Additionally, as researchers aim to refine the technology and improve accuracy, the commitment to open-source AI development suggests that collaboration with the broader AI community will be crucial in accelerating progress towards viable communication solutions. 1. The development of the electroencephalogram EEG. In the early 20th century, Hans Berger developed the electroencephalogram EEG, a groundbreaking technique for measuring electrical activity in the brain. This invention marked a significant advancement in neuroscience and laid the groundwork for future research into brain-computer interfaces. EEG technology has been used for various applications, including diagnosing neurological disorders, understanding brain functions, and more recently, enabling non-invasive communication methods for individuals with disabilities. 2. Brain-computer interface research at the University of California, Berkeley. In the early 2000s, researchers at UC Berkeley developed a brain-computer interface that allowed paralyzed individuals to control a computer cursor using their thoughts. This research utilized implanted electrodes to detect brain activity associated with movement intentions. It demonstrated the potential for restoring communication and mobility to individuals with severe motor impairments, paving the way for further advancements in neurotechnology and brain-to-text systems similar to Meta's recent studies. 3. Neuralink's brain-machine interface trials. Founded by Elon Musk in 2016, Neuralink aims to develop advanced brain-machine interfaces (BMIs) that can enable direct communication between the brain and external devices. The company has conducted trials involving implanted devices in animal models showcasing the ability to decode neural signals and translate them into actions, such as controlling a computer or robotic limb. Although still in the experimental phase, Neuralink's work parallels Meta's efforts in exploring thought-to-text technology, highlighting the growing interest and potential in the field of neurotechnology. Future outlook: revolutionizing communication through thought-to-text decoding. As we look toward the future of communication technology, Meta's recent breakthroughs in thought-to-text decoding present a compelling vision of what is possible. With an 80% accuracy rate achieved through non-invasive brain recordings, the implications for individuals with communication impairments are profound. This technology is not just a theoretical exercise, it has the potential to revolutionize how we interact with each other and with machines. 1. Enhancing communication for the impaired. One of the most immediate applications of this technology is in the realm of assistive communication devices. For individuals who have lost their ability to communicate due to neurological injuries, such as stroke or ALS, a reliable thought-to-text interface could restore their capacity to express themselves. In the coming years, we can expect advancements that will make these systems more practical and accessible. Miniaturization of equipment. As research progresses, we anticipate the development of smaller, more user-friendly devices that can be used outside of specialized clinical settings. Innovations in technology could lead to wearable brain-computer interfaces (BCIs) that are discrete and portable. Integration with AI assistants. Thought-to-text technology could be integrated with existing AI assistants, enabling users to communicate effortlessly with smart devices, enhancing their independence and quality of life. 2. Broader applications in everyday life. Beyond assisting those with communication challenges, thought-to-text decoding could find applications in various sectors. Education. Students could use this technology to take notes or engage in interactive learning without the physical limitations of typing or writing. This could particularly benefit those with learning disabilities or physical impairments. Gaming in virtual reality. Imagine a gaming experience where players can control their characters or navigate virtual worlds through thought alone. This could create immersive experiences that are currently unimaginable. Creative writing and content creation. Writers and content creators could utilize thought-to-text systems to brainstorm and draft their ideas without the constraints of typing, potentially leading to new forms of storytelling and expression. 3. Advancements in neuroscience and AI. The research conducted by Meta not only opens doors for communication but also enhances our understanding of the brain's cognitive processes. As researchers continue to decode how thoughts translate into language, we may witness breakthroughs in several key areas. Understanding language processing. A hierarchical organization of language production revealed by Meta's studies can inform the development of more sophisticated AI language models. This could lead to systems that understand context better and produce more nuanced responses. Neuroscience research. Continued exploration of brain activity during language production will provide insights into how various neurological conditions affect communication, leading to better targeted therapies. 4. Ethical considerations and privacy. As with any emerging technology, ethical considerations will play a crucial role in its development and implementation. The ability to decode thoughts raises significant questions about privacy, consent, and the potential for misuse. Future developments must prioritize user autonomy, ensuring that individuals maintain control over their data and the ability to opt in or out of thought-to-text systems will be essential. Regulatory frameworks. Governments and regulatory bodies will need to establish guidelines that protect individuals from unauthorized access to their thoughts and brain data. 5. Challenges ahead. While the potential is immense, several challenges remain before thought-to-text technology can be seamlessly integrated into daily life. Technical limitations. Current systems, while impressive, still face hurdles in decoding thoughts with perfect accuracy. Continued research is required to enhance the technology's reliability and performance. Cost and accessibility. The current equipment used in research settings is expensive and not widely available. Future innovations will need to focus on reducing costs and making technology accessible to a broader population. Conclusion. The future of communication, as envisioned through Meta's advancements in thought-to-text decoding, is one filled with possibilities that extend far beyond assisting those with disabilities. As we refine this technology, enhance our understanding of the brain, and address ethical concerns, we stand on the brink of a new era in human interaction. The integration of AI with neuroscience will not only transform communication but could also unlock new dimensions of understanding the human experience itself. As we continue to explore these frontiers, collaboration among researchers, technologists, and ethicists will be vital in shaping a future that respects individual rights while harnessing the power of technology to enhance our lives.